Welcome. Today we'll dive into the world of exponents and exponential functions, essential concepts in algebra and beyond. Whether you're studying for a test or just brushing up on your math skills, this video will provide a clear and structured explanation. Let's get started. Exponents are a shorthand way to express the repeated multiplication of a base number. Here we can see the base, and here we see the exponent. This base and exponent combination creates a power. If a is a real number and n is a positive integer, then a to the power of n would be a times a times a times a times a n times. So a is multiplied by itself n times. For example, if we have 3 to the power of 4, it would be 3 multiplied by itself 4 times, which gives us the value 81. However, exponents are not always positive. We also deal with 0, negative, and fractional exponents, and these have special rules. A to the power of 0 is 1, no matter what a is, and a to the power of negative n is 1 divided by a to the power of n, which means we take the reciprocal of a to the power of n. Think of fractional exponents as a combination of powers and roots. The denominator of the fraction tells us which root to take, and the numerator tells us what exponent to raise it to. Let's take an example. Let's say 8 to the power of 1/3. The denominator is 3, so we take the cube root, and the numerator is 1, so we raise it to the power of 1. So there's the cube root of 8, which gives us the value 2. Let's talk about some more laws. The exponents follow specific rules, which make calculations easier. Let's go through them one by one. The product rule. A to the power of m multiplied by a to the power of n is a to the power of m plus n. For example, 2 to the power of 3 times 2 to the power of 4 is 2 to the power of 7, because 3 plus 4 is 7, and this gives us the value 128. Quotient rule. A to the power of m divided by a to the power of n is equal to a to the power of m minus n. For example, 5 to the power of 4 divided by 5 to the power of negative 2 is equal to 5 to the power of 6, because 4 minus minus 2 is equal to 6. And this gives us the value 15,625. Power rule. A to the power of m to the power of n is equal to a to the power of m times n. For example, 2 to the power of 2 to the power of negative 3 is equal to 2 to the power of negative 6, which is 1 over 2 to the power of 6, as we saw before with the negative exponent rule. And this gives us 1 over 64. Let's talk about exponential functions. Exponential growth. We have a function f of x equal to a times b to the power of x, and b is greater than 1. This means that the function will curve upwards rapidly as x increases, and we can see this here. Let's take an example. F of x equal to 2 times 3 to the power of x. As b is greater than 1, the function will curve upwards rapidly as x increases. Exponential decay. They have the same function format, a times b to the power of x, but b is between 0 and 1. That means they curve downwards rapidly as x increases, and we can see this in this graph here. For example, 5 times 0.5 to the power of x would curve downwards rapidly as x increases. It's important to know that these functions will never reach 0, but will get infinitely close. Here are some applications of exponential functions. Population growth. P of t is equal to p times e to the power of rt. where P is the initial population, R is the growth rate, and T is the time. Radioactive decay. A equal to small a times e to the power of negative kt, where a is the initial amount, k is the decay constant, and t is the time. Compound interest. A is equal to p times 1 plus r over n, in parentheses, to the power of nt, where p is the principal, r is interest rate, n is the number of times compounded per year, and t is the time in years. Here are some graphs. Compound interest graph. As you can see, the principal is just a flat line, and interest without any compounding is just also going to be a line, and compound interest is an exponential growth function. As x increases, the value we have in the bank account, or how much money we have, is going up rapidly. This is an example of radioactive decay. As the function is decreasing rapidly, the function value is decreasing rapidly as x increases. So this is an exponential decay function. And here we have an example of population growth, and this is an exponential growth function. So in summary, exponents follow specific rules: product, quotient, power, zero, negative, and fractional. Exponential functions model rapid growth or decay. Some applications include finance, population studies, and radioactive decay. Thanks for watching. Be sure to practice with some problems to reinforce these concepts. See you next time.